Hi goers, welcome to the Chapter 3 review video. Today we're going to be talking about stereochemistry. And before you even talk about anything, I just want to give a little bit of a disclaimer. So stereochemistry is something in organic chemistry that does not go away. It's going to be constantly brought up with every single reaction that we see for the remainder of the semester in Organic 1. If you're moving on Organic 2, it is constantly talked about over and over again. So this is something I really want you guys to understand and get those details down because it will come and bite you later on. So definitely make sure this is something that you know pretty well. Okay, so stereochemistry, what is it? Well, stereochemistry is basically just a branch of organic chemistry that deals with the specific, 3D arrangement or configuration of specific substituents. So we learned what a substituent was. So, if I had, this plain like carbon chain and, we had maybe like, let's just say an ethyl group coming off of it. And notice how I made that a wedge. So stereochemistry is going to explain what does that, ethyl group on a wedge mean, So we're basically dealing with how these substituents are placed in 3D space, and that is this kind of topic that we're dealing with. So just something to bring back to the front of your brain. We saw, I guess, back in exam 1 when we were first doing, different ways to draw molecules, we saw something that looked like this. And this is called a nata projection. So let's just, fill some stuff in here. So maybe like a fluorine up there. Let's just say a bromine there. We'll just put a whole bunch of things on there. So what does this mean? Well, the wedge thing, the wedged chlorine means that it's coming out of the page and to my face. And the bromine that's on a dash means that it's going into the page or like through the screen that you're watching this on. So, that's a specific type of stereochemistry or stereocenter where, that chlorine is oriented out specifically, and that bromine is oriented inward. So that specific 3D arrangement is what we call stereochemistry. Okay? So what is a stereoisomer? So stereoisomers are molecules that have the same exact, molecular formula, but they differ in their 3D configuration of their substituents. So I guess I could just say same molecular formula, but just differ in their 3D arrangements of substituents in space. Sorry, maybe I'll just put different here. So, same molecular formula, but they differ in their 3D arrangement of substituents in space. Okay? So we're going to practice a whole bunch of example problems of seeing different types of stereoisomers and how to identify those. Okay? So overall, stereochemistry is just this branch in organic chemistry where we're going to talk about this 3D orientation of substituents, and stereoisomers are specific sets of molecules that have the same exact molecular formula with the same exact substituents. However, the placement of those substituents can differ, and this is a type of isomer that we're going to see. Okay? So, what exactly is a stereocenter, or we can also call that a chiral center? And the definition of a chiral center is an sp3 hybridized carbon with 4 different substituents attached to it. So, if I were to zoom in over here and write that out, it is an sp3 carbon with 4 different substituents. Okay, so think back to exam 1 when we're categorizing the hybridization. So, let's look at this molecule over here. So this carbon, we see that we have one area of electron density, the second, the third, and the fourth. So 4 areas we said was definitely an sp3 hybrid, and more specifically, you can see that we have 4 different substituents attached. We have a chlorine, a bromine, a hydrogen, and a methyl group. So this definitely satisfies all that criteria for a chiral center. So we definitely know that this is going to be a, stereocenter. Okay, so what does that mean? What does chiral mean? So chiral basically means that there can be a mirror image of this molecule. So this kind of glossy background is the mirror image, and it's non-superimposable, meaning that it's not able to be placed directly on top of the original molecule and it being the exact same. So, we see that we have this line, down here, and we can see how this is the exact mirror image. But if I were to pancake flip this molecule on the right over, would it be able to just completely overlap and be the exact same thing? So let me just draw that out here. Let me draw the nata projection for you. So if I were to pancake flip, so let's just say pancake. Oops. Okay, if I were to pancake flip that, it would look something like this. Oops. Okay, so if I were to pancake flip this around, you can see that if I were to place this molecule back on top, that methyl group went from the wedge in the first picture to a dash in the second picture. And that hydrogen went from a dash to a wedge. So you can see that this mirror image is non-superimposable. And that's a property of chiral molecules. So, take a minute to look at your hands for a second. If you were to place your hands directly out in front of you, kind of like you were a mummy, you would see that I can put an imaginary line between my left and my right hand, and those are definitely mirror images of one another. But if let's say I was trying to pancake flip my right hand, so that I can superimpose it on my left hand, you can see that it definitely is not the exact same. I'm looking at the palm of my hand, while the hand behind me, I guess my left hand, is going to be, the back face of my hand. So you can see that your hands have this chirality property to them. So, all that this chirality, conversation means is that molecules, specifically sp3 carbons with 4 different substituents, observe this phenomenon in nature where the mirror image is non-superimposable on it. Okay? So if we were trying to identify stereocenters in a molecule, all we really are looking for is this sp3 carbon with 4 different substituents. So let's practice that. So the drug simvastatin is used to lower cholesterol levels in patients. So, it's a big family of drugs in the statin family. All those drugs are used to lower cholesterol. Circle all the chiral centers in the molecule depicted below. So let's just start from the top and work our way down. So we are looking here for an sp3 carbon with 4 different substituents. So we're going to go one at a time. Okay, let me zoom in for the top ring. So, don't forget that there's all these imaginary hydrogens here. So, if we're looking at just the top ring exclusively, so let's just look at the top fragment, we're looking for a carbon with 4 different substituents. So, this carbon, would that work? Well, no, that carbon definitely would not be a chiral center because we need it to be sp3 hybridized. And, if we were to classify the hybridization of that carbon, it's definitely sp2. So that definitely does not work. Okay, so then if we were to move over to the left, we would see that we have, these 2 imaginary hydrogens that we need to draw in. So yeah, that's definitely an sp3 hybridized carbon because, we have this carbon-carbon bond on the left, the carbon-carbon bond on the right, and then the 2 carbon-hydrogen bonds. However, are all 4 of those substituents different? Well, no, we just drew 2 hydrogens. So this is also definitely not a chiral center. Okay, so keep moving to the left. We see that we have, this carbon right here with an imaginary hydrogen. We see that there's also a hydroxyl group attached to it, and we also see that we have this left side of the ring, which is crazy, and we have this right side of the ring, which is also, this crazy thing with some sort of oxygens attached. So clearly this is an sp3 hybridized center with 4 different substituents, so this would be our first chiral center. Okay, so again, keep moving down. We see that we have 2 hydrogens here, so that definitely would not be one. Okay, so keep moving over here. If we draw that hydrogen, we see that, yes, we definitely have a chiral center. It's sp3 hybridized, and we see that all 4 substituents are clearly different. So this would be another example. All right, so that was just, me going slowly through all of these. But take a second, pause this video if you need to look at the rest of the molecule, and determine where else are those chiral centers. And I'm just going to fill those in right now. Okay, so I hope you understood all of those. I think everything's pretty obvious, except maybe this one was a little confusing. Maybe this one was a little confusing, that carbon in the middle. So if I were to zoom in and just kind of analyze that carbon a little bit more, we see that we do have a hydrogen that's not drawn in. So we have this, attached to this carbon, we have the left fragment. So I guess let me highlight this in orange. So we have this left fragment. Then we have this right fragment. And then don't forget that we also have the fragment that's below. Okay, so it's clearly 3 different things. Also, there's that hydrogen, so that's the 4th thing. That's why that was the chiral center as well. So that one was kind of tricky, but I think everything else you pretty much should be capable of getting. Okay, so definitely be able to identify chiral centers on the test. Okay, so let's move on. So what is a chiral molecule? So we said that, this chiral center is a specific, sp3 hybridized carbon with 4 different substituents, and we can make a mirror image of it, and once I pancake flip that mirror image, try and superimpose it on the original, it's not going to be able to do so. So we talked about that. But what really is a chiral molecule? And chiral molecules are basically these molecules that have the ability to rotate a plane of polarized light. What does that mean? If I were to shine a flashlight, polarized, well, that's not polarized, but let's just say the flashlight is polarized. If I were to shine that light at a molecule, maybe of a specific configuration, that light would actually be bended at a certain angle, maybe let's just say to the right. And if I were to pick the opposite configuration of that, let's just say I flipped the wedges and the dashes, kind of like when I do in a mirror image, and shine the light at it, it would flip to the left. So the fact that we have these chiral molecules means that it has the ability to rotate light. And this device is called a polarimeter. So polarimeter. I hope I'm spelling that right. So it's a polarimeter, and you can see that we have some sort of light source that we're shining through this polarizing filter. So we have this, one stream of light, and this kind of chamber over here is filled with a solution of, our specific, I guess, molecule that we're analyzing. And based on the degree of rotation, so over here it's set at 0, and let's just say it comes out over here, this angle, theta, actually, no, it's called alpha, excuse me, this angle alpha is going to tell us, how much of that, how much light was rotated from being exposed to that chiral molecule. Okay, so we use this device called a polarimeter just to see if a molecule is chiral, meaning that it does rotate light. The angle alpha doesn't really tell us much in terms of like the identity of the compound, but it will definitely tell us if a chiral molecule is present. Okay, so let's practice chirality. So there are a few guidelines that we should go through. If a molecule has one chiral center and only one chiral center, it's always going to be chiral. So one chiral center means that it's always going to be chiral. Okay, if you have 0 chiral centers, it's definitely going to be achiral. Okay, and if you have 2 or more, it may or may not be. Maybe. So we have to look for some other things if we have 2 or more chiral centers. And what we're looking for is something called a sigma plane. Okay? And sigma just comes from the letter S, and we're looking for symmetry, basically. Okay? So let's just practice all these guidelines with these molecules below. So circle all the chiral molecules. There may be more than one. Okay, so the first one we want to do is identify the chiral centers. So if we were to look at that ring, okay, let me just zoom in over here. We're looking at this ring. I'm looking for a carbon that's sp3 hybridized with 4 different substituents. So it's obvious that this carbon, this carbon, this carbon, this carbon, and this carbon are not chiral centers because they all have at least 2 hydrogens attached to them. So, maybe if I was thinking about that last carbon up here, is this a chiral center? Well, it looks like it is. We have that thiol group, that SH group. We have that methyl group, CH3, but it's not a chiral center because the left side of the ring and the right side of the ring are the exact same. So it does not satisfy that criteria of 4 different substituents. Therefore, there are 0 chiral centers. So what did we say what happens when there's 0 chiral centers? Well, it's always going to be achiral. So that means that that molecule as a whole is not chiral. Okay? Excuse me. So if we were to look at this next molecule, we could see that we definitely have a carbon in the middle. Okay, this carbon over here. And that carbon doesn't have 4 different substituents attached to it. Well, we have this carboxylic acid, that's group 1. We have a methyl group, that's group 2. Ooh, but we have 2 hydrogens. Yikes. So that is not 4 different substituents. So again, this is not a chiral center. So we have 0 chiral centers again, or it's achiral. Okay? So it looks like it's chiral with the wedges and dashes. Do not be fooled. You have to satisfy all those criteria that we discussed above. Okay? So let's move to the next one. So over here, we see that we have this ester functional group. So this carbon definitely is not a chiral carbon because it has 3 hydrogens attached to it. This carbon is not a chiral carbon because it's sp2 hybridized. This carbon is not a chiral center because there are 2 hydrogens attached. So now we're thinking about this carbon over here. So this carbon has this whole left ester group attached to it. It has an imaginary hydrogen that's not drawn in. But it's not a chiral center as well because there are 2 methyl groups attached to it. So this molecule as a whole has, again, 0 chiral centers, therefore achiral. Okay? And this one was kind of obvious with the chiral centers because there was no wedges and dashes shown. Okay, so let's move down over here. So we see that, this carbon, it looks pretty obvious to me. It like kind of pops out of the page, and it shows that we have an ethyl group on a wedge. So this carbon has also that hydrogen. So we have 4 different groups attached. We have an ethyl, a methyl, an isopropyl, and a hydrogen. So yes, this is an sp3 hybridized carbon with 4 different substituents. So this is most definitely a chiral center, and there's only one. So this is one chiral center, and the rule we always said was if there's one chiral center and only one chiral center, it is definitely going to be a chiral molecule. Okay? So keep going. So over here we have this molecule. We have a thiol group and a fluorine, and we see that this carbon is going to be, sp3 hybridized as well because there's a hydrogen not drawn in. So we have a methyl, a thiol, a hydrogen, and that whole fluorine substituent. So yeah, that is definitely one chiral center right there. But also that fluorine has a dash, so let's look at that. So we have a methyl, a fluorine, the thiol group, and that imaginary hydrogen attached. So that's also another chiral center. So in this molecule, we actually have 2 chiral centers. So we said if we have 2 chiral centers or more, it may or may not be chiral, and we have to look for one more thing. Is there a sigma plane, or is there symmetry? So there definitely is not symmetry here because there's no lines that I can draw through this to, fold it in half and get the mirror image. So this is definitely no symmetry here. So we can go ahead with that assertion that this is a chiral molecule. Okay, so let's move on to the last example. So we see that we have 2 chiral centers. We have this carbon because there's a methyl, the thiol group to the right, the thiol group directly attached, and that hydrogen. So that is definitely a chiral center. And then over here, we see that we also have a thiol group directly attached, a methyl group, and that thiol group that's not directly attached, and the imaginary hydrogen. So we see that we have 2 chiral centers. So we said that may or may not be chiral, but we have to look for one more thing. Is there that sigma plane? So at first glance, we see that there is no sigma plane. There is no way that I can draw a plane of symmetry to fold it in half and, get the same molecule. Okay? But if you said that this molecule was achiral, if you said this molecule was chiral, you would be wrong. And the reason that is you have to remember to rotate. If I were to rotate around that sigma bond and we said that was a characteristic features of alkanes, you would get something that looks like this. Because if I rotate this thiol group down or forward, that's going to form a wedge. And now it's obvious that there's that sigma plane. So this molecule as a whole is achiral, even though it has 2 chiral centers. All right? So I hope that gave you a little bit more, insight on determining what chiral molecules are. I did want to say one more thing, that this molecule at the end is given a specific name called meso. And what all that meso means is that it's a molecule with chiral centers, but it's overall achiral because of that plane of symmetry. Okay? So whenever you see these molecules where it is achiral because of that sigma plane, you can call them meso. Okay, so that kind of talks about chirality, and now let's assign, specific rules to, identifying different types of chiral centers. Okay, so we're going to use something called the Kohn-Ingold-Prelog rules for assigning absolute configuration. I know it sounds a little daunting, but it's not that bad. So you can see this is a snapshot from your book. As, we're going from left to right, we can see that we're increasing priority, and that's denoted by that arrow. But what specifically is deciding what this priority is? So we see that there's these red numbers up top. There's 1, 6, 7, 8, yada, 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 all the way up. So what does that mean? Well, that is the atomic number, okay? So that's the atomic number of these atoms, the atoms that's directly in contact, with that bond. So the hydrogen is first on the periodic table, so it has a 1 atomic number, meaning that there's 1 proton there. And then if we move up the methyl group, that carbon is 6 in the periodic table, so there are 6 protons there, and so forth and so on. So, as we increase, the atomic number, or going down the periodic table, or going across the periodic table, we are going to increase priority. So atoms with higher atomic numbers immediately have increased priority. So that's rule number 1. Then if we move to the second arrow that's right below it, we see that what happens if the substituent attached to that carbon all has the same atom. Let's just say it's a CH2 all the way down. So you want to look for the first point of difference. So yeah, the CH2 is all in common, so I can basically just ignore that. And then I want to look for the first point of difference, which would be the hydrogen, this carbon, this nitrogen, oxygen, and so forth. So you just want to use that same rule of atomic number being higher priority, but you just want to find the first point of difference. Okay. So once you rank all the substituents on the carbon, 1, 2, 3, and 4, you want to do something like this car wheel drawn below. So I thought this was kind of cool. It was from your book. You want to orient the fourth substituent away from you. So it's like if you're driving a car and that, I guess, I don't even know what you're going to call it, that rod that holds the steering wheel in place, that thing needs to be oriented away from you. And then you want to trace, the priority that you numbered everything in. Does 1, 2, 3 go in a clockwise manner towards the right? So something like that. Because if it does, we're going to call it R. And if those priority substituents go, 1, 2, 3 counterclockwise to my left, so something that looks like this, that's we're going to call an S configuration, okay? So, we know how to identify chiral molecules now, and we know how to identify chiral centers, so the next step is to look at these substituents attached to a chiral center, and then give these priorities to them, and then say, this is an S configuration, this is an R configuration. So let's look over here. Let's practice that. So the drug oseltamivir is a medication. It's also called Tamiflu. A lot of people take this medication. It's used to treat the flu. The molecule has 3 chiral centers labeled A, B, and C. So now let's assign priority to those substituents and determine the absolute configuration, meaning is it R or is it S? So let's just take these one at a time. Let's look at A. So I'm going to draw in, our substituents that aren't as obvious. So let's just draw in that hydrogen on a wedge. And let's go through and number the substituents. Okay, so we're looking at this carbon. So directly attached to this carbon is an oxygen, a hydrogen, a carbon, and a carbon. Okay? So out of those 4 atoms, oxygen, carbon, carbon, and hydrogen, which one has a higher atomic number on the periodic table? Well, it's oxygen. Okay? So that means that this group attached is going to be number 1. Okay? And hydrogen we know has an atomic number of 1, so that's immediately going to be the smallest possible one, so we can just say that this hydrogen is immediately going to be my worst priority, or priority number 4. So between the 2 other substituents, we both ran into a carbon first. So let's look at the next point of difference. So what's attached to that carbon would be a hydrogen and another carbon. So there's this hydrogen here, and then there's carbons here, and then the next one would be a nitrogen over here. Okay? So because that nitrogen is attached, that's like a higher atomic number than a carbon or a hydrogen would be. So this group would be priority number 3. Okay, and this group would be priority number 4. I'm sorry, priority number 2. Okay, so that is the correct assignment for these specific, substituents. So now, once you assign the priority based on atomic number, all you want to do is orient it so that that 4th group is away from you. Okay, so in this specific configuration, we drew that hydrogen on a wedge. So that means it's coming out at me. So that's the exact opposite of what we wanted. We wanted to orient this so that it's away from us. So we can either do one of 2 things. I can, pick up the screen and look from behind it and trace it, or I can ignore the fact that it's on a wedge, trace it, and just remember to flip the configuration. So I'm going to do the latter. So if I were to ignore the fact that that hydrogen is on a wedge and trace it, I see that going from 1 to 2, 1 to 2 to 3 is definitely in a clockwise manner, so a counterclockwise manner rather, and that would be an S configuration. Okay, but remember that's not what we wanted. We wanted that hydrogen or that 4th group to be on a dash or oriented away. So you need to remember to flip it to an R. Okay, and I'm not just remembering that rule. It makes sense because if I were to look at it from the other orientation or from the other side of the room, then that would be the opposite configuration or going in a clockwise manner, R. Okay, so A is definitely an R configuration. And you'll get really fast at identifying these. I'm just going slow for you guys. So R. So let's look at B. So for B, we see that we have this carbon right here, and it's attached to a carbon, a nitrogen, and there's a hydrogen. So out of the carbons, the hydrogens, the nitrogens, obviously the nitrogen is going to be higher priority based on the atomic number. So that's definitely number 1. Okay? So, and we know that hydrogen is going to be, let's just draw it in on a dash, that's definitely going to be number 4. Okay? So the next ones we have to consider are carbons to an oxygen or carbon to a nitrogen. Okay? And the answer is, which one is better? Well, the carbon to the oxygen would clearly be better than the carbon to the nitrogen, because the carbon to the oxygen has a higher priority than the carbon to nitrogen, because oxygen has a higher atomic number than nitrogen does when we go across the periodic table. So if I were to, C is that 4th group oriented away from me, yeah, it's on a dash. So this is the actual good configuration that we wanted. So if I were to trace 1 to 2 to 3, oops, excuse me, I wrote 4 twice. That would be number 2, and that would be number 3. I apologize. So if you were to trace that, it'd be 1 to 2 to 3. That's clockwise, and it's fine that the way that it is, so it's R. Okay, so B is an R configuration. Let me just draw it over here. So let's consider C. So for C, we have this carbon we're analyzing, and there is a nitrogen, a carbon, and that hydrogen. So we said that that hydrogen is going to be on a wedge because that nitrogen is on a dash, so that's clearly number 4. And that nitrogen was clearly number 1. So now we have to decide, is the carbon with the hydrogens attached to it more important than the carbon with the nitrogens attached to it? Well, no. So this is clearly number 2. The carbon with the nitrogen is probably more important than the carbon with the hydrogen. Okay? So let me just erase all this clutter. Looks crazy. Okay, so if I were to, trace this orientation, that's 1 to 2 to 3, oops, 1 to 2 to 3, that would be a clockwise orientation, or R. But was that 4th group oriented away? Well, no, it was a wedge. So it definitely needs to be inverted, so it should be an S. So if I were to, rewrite all of these out, A, B, and C, the answers were R, R, and S. So definitely take some time, pause the video if you need to, identify those chiral centers and assigning priority. Okay, so let's move on. So what does that mean? What does R and S mean? Well, it's just a specific way to assign, types of chiral centers, meaning that this clockwise orientation of priority is one specific orientation, and the counterclockwise priority is a different orientation. And that has specific consequences for the types of isomers that we can see between molecules. Okay, so what is an enantiomer? So let's just go over a couple of definitions. So an enantiomer is a non-superimposable mirror image. And we can identify by noticing all chiral centers invert. Meaning, we just figured out what R and S means. So that's basically assigning a specific name to it. So if the R's go to S's and all the S's go to R's, that is the definition of an enantiomer. This can be also commonly noted if I see wedges going to dashes and those dashes all going to wedges. Okay? So every single chiral center has to invert their configuration, either R to S or S to R, or wedge to dash or dash to wedge, to be an enantiomer. It is a non-superimposable mirror image. So for instance, if I were to take my hand, assuming that my hand was a chiral carbon, right? Those are mirror images, my left and my right hand of one another, and if I were to go and superimpose them on one another, my left hand would be like, let's just say, an R configuration, and my right hand would be the S configuration, and that clearly was a non-superimposable mirror image, so that's a way to explain enantiomers. The R to the S switches, the wedge to the dash switch, or the fact that they are non-superimposable mirror images, all interchangeable. So what is a diastereomer? So a diastereomer is a non-superimposable non-mirror image. So the difference from the one above and below, is the fact that enantiomers are mirror images and diastereomers are not mirror images. Okay, so we could identify this by seeing partial inversion of chiral centers, meaning Some go from R to S and S to R, but not all. Not all. I guess that's important to write. Not all of them do. Okay, so that's what makes it the non-mirror image. The fact that not all chiral centers invert mean that, this cannot be a possible mirror image. So that means, maybe we'll see all the wedges go to dashes, but maybe one of those dashes maintains a dash configuration. So that's the ways that we can identify that. So again, maybe we'll see this where like all the R's go to S's except for one, so only partial inversion. So those are specific types of stereoisomers. Remember at the beginning of this video we talked about a stereoisomer is a molecule with the same molecular formula, with the same substituents, however they differ in their 3D arrangement, meaning wedge, dash, dash, wedge. And now I think it's coming a little bit more clear what is an enantiomer and what is a diastereomer. Okay? So let's just practice that over here. Given the pairs of molecules below, identify the relationship as identical, non-enantiomers or diastereomers. And this is extremely important. I cannot emphasize this enough. You're guaranteed questions like this on your test. You'll be given pairs of molecules that look different, and you need to be able to, look at them and see, hey, is this an enantiomer, is this a diastereomer, be able to convert between Fishers and Chairs and Newmans and all that stuff. So be comfortable with different representations of the same molecule. Okay, so if I were to look at the molecules in A, okay, so these molecules, one is a nada projection and one is line angle, and I see that there's only one chiral center. So in a situation like this, sometimes it helps people to draw that nada projection maybe in, line angle, but I don't see the benefit of that. Since there's only one chiral center, it would just be best, in my mind, to just assign R and S and see if that maintained its configuration in the second picture. Okay? Also, the first thing you really want to do is see if the molecular formulas are the same, because if the molecular formulas are not the same, then immediately you know they're not related. Okay? So clearly we have the same molecular formula here. We have this aldehyde up top, so that's the aldehyde over here. We have that carbon with a fluorine attached, there's an ethyl group attached to it, and there's that imaginary hydrogen. Okay? So clearly these are the same exact molecules. Maybe, there's some sort of isomers of each other. So let's assign priority. So we see that we have a fluorine directly attached, so that's priority number 1. We see that we have a hydrogen attached, so that's priority number 4. We see that we have, a carbon bound to an oxygen, so that's probably priority number 2. And then we just have other carbons attached here in an ethyl group, so that's carbon number 3. Okay, so now that we assigned all the priority, let's trace this. So 1 to 2 to 3. But we need to place it where that fourth group is away from us. So this one's a little bit different. We haven't seen this one before, where, how the fourth group is in plane. So we can do a couple of things. I can literally pick up my screen and put it in between my eyes and, basically look at it from a side-on view, because that's equivalent to putting that hydrogen, on away from us, or that, the fourth priority as far away as possible. So if I were to do that, I can kind of trace it really quickly and see that the first group is to my right, the second group is up, and the third group is to my left. So if I were to trace that, it would have been something like this. So that would have been most definitely an S configuration, okay? But, maybe that doesn't help. And what if you wanted to draw maybe like a Newman projection? So let's just look down, that carbon-hydrogen bond, because that's the same thing as saying that that hydrogen or fourth priority is away from us. So, if you didn't like, picking up the screen and looking at it like that, I can draw the Newman. So on the first carbon, we have our priority number 2 going up. We have our priority number 1 to my right, and we have that priority number 3 to my left. And that priority number 4 is, directly behind it. So if I were to trace this Newman, it goes 1 to 2 to 3, back to 1. And that is S. So that also worked. So we could assign the chiral center in the first molecule for A as S. So let's do the same thing for, the line angle notation. So if we're to do the same thing for the line angle notation, we know that the fluorine is 1, this group is number 2, this group is number 3, and that hydrogen is group number 4. So if I were to trace the priority of this, it would be 1, 2, 3, and that's definitely S, okay? But was that fourth priority on a dash or away from us? And no, it's not. It's on a wedge or coming towards us. So, you can either look at it from the back face, or you can just remember that S goes to R if your fourth priority is not in plane. Okay, so what does that mean? Well, we had one chiral center here, and it completely inverted from S to R, so that was a definition of an enantiomer. So these are enantiomers. Okay, so what does that mean now? Let's piece it all together. Well, these are chiral molecules because they have a sp3 hybridized carbon with 4 different substituents. More specifically, there's only one chiral center, so that's why we know it's chiral. And the configurations of their arrangement of these substituents in 3D space are different. That fluorine and that ethyl group switched configurations from the left to the right molecule. So that means that they are a type of isomer. They have the same molecular formula, they have the same substituents, but they differ in their connectivity in space. Okay? And the enantiomer is just the name we're going to give to the isomer where all of those stereocenters are different. And since there's only one, it's obvious. Okay, let's look at B. So for B, you can assign priority to both of these, substituents. So I would say that I'm going to do this fast now. So just draw on that hydrogen. So fluorine is 1, hydrogen is 4. The sulfhydryl group to the right, it would be number 2, and that would be number 3. So if I were to trace that, that's going to be an R configuration. Okay, so that's an R configuration. If I were to do it for the sulfhydryl group, it's definitely 1 over here, 2 over here, 3 over here, and that hydrogen is going to be 4. So if I were to trace that, configuration, that's going to be R, but don't forget that the hydrogen's on a wedge, so it's really an S configuration. Okay, so that first chiral center was an R, and the second chiral center was an S, so that's the first, set of priorities. So let's look at our next molecule and assign priority as well. So that fluorine, we said that was 1. We said that the group to the left, to the right was 2. The methyl was 3, and then hydrogen was 4. So if I were to trace that, that's going to be an R configuration, and that hydrogen was oriented away, so that's fine. So if we were to do this one, we know that sulfur is 1. The left side would be 2. This would be 3, and then hydrogen would be 4. So 1, 2, 3. If I were to trace that around, that's going to be a S configuration. So that S configuration actually goes to an R configuration because that hydrogen was on a wedge. All right. So you can see that one of those chiral centers stayed the same, so R to R, and one of them didn't, so S to R. Okay. So that is a specific example of a diastereomer. Okay, and let's say, assigning priority took too long and I didn't want to do that on a test. Maybe I'm not that comfortable with assigning priority. Well, this is what I would do. I would rotate the molecules into both cis conformations, okay? So the right one is clearly already in its cis conformation. So if I were to rotate around this bond, the cis conformation would look something like this. And now you can see that since they're the exact same, orientation, I can just see, well, yeah, the fluorine maintained the wedge configuration, so that chiral center did not invert. And then we see that the sulfhydryl group did invert, so that's partial inversion of the chiral centers, and that could have been a very, very easy shortcut to realize that these are diastereomers. All right, so personal preference, if you're fast enough, I recommend, on the test, just doing wedges and dashes, figuring that out, and then if you have time at the end, then going back and assigning priority just to further, prove your point that you were right. All right, so now C is probably the hardest. So people don't like chairs to begin with, but you need to be ready to answer questions about chairs, in terms of diastereomers and enantiomers. So my recommendation for you would be to convert all chairs back into their cyclohexane planar form. Okay, so let's just say I'm going to pick, that methyl group on top to be carbon number 1. Okay, and maybe I'll just draw this over here. And if I were to number the carbons over here, we see that this carbon 1 is clearly down and out of plane, so that's 1, 2, 3, 4, 5, 6. Okay, so our numbering is all consistent. So let's just also do that over here. Okay, so on carbon number 1, we are at an equatorial position. So to be equatorial at that position, it must have been on the wedge. Remember, the trend is, for this specific chair conformer, down, up, down, up, down. So if the methyl group is equatorial, it clearly didn't match the down stereochemistry configuration, meaning a dash. So it should have been a wedge in the starting material. Does that make sense? So again, since carbon 1 is oriented down, the thing that's on the down substituent, meaning the dash, would be axial. So since the CH3 group is equatorial, it must not have been that dash, it had to have been the wedge. So it's a wedge CH3. Keep going. Down, up, down. So on carbon number 3, we're also down. But that fluorine is clearly equatorial. So it couldn't have been that dash down thing. It must have been that equatorial thing. Or that something like that. Okay, so you can see that it was down, up, down, okay? Then if we go to carbon number 4, it should be down, up. So on carbon number 4, it should be up. So is that, bromine axial up? No. So it must have been a dash on carbon number 4. Okay, so if I were to look at the chiral centers here and see if they inverted, we see that carbon number 1 inverted, carbon number 3 did not invert, but carbon 4 did. So what would be the relationship between these two? These would be diastereomers as well. Okay, so that I hope that helped, figure out, I guess, these types of molecules in stereochemistry. It's definitely a tricky topic, but you're going to get so good at it with practice, and it does keep coming up, so please, please, please practice this and get this down. It is not a time to just, throw this under the rug. Good luck studying, guys.